Assalamualaikum and good morning. We are from the BERT1333 going to present on the topic of transfer function.
What is transfer function? The transfer function is defined as the ratio of the Laplace transform of the output to the input. It is denoted by hashes and is primarily used in the analysis of the linear time invariant system. By using this function, complex differential equation can be converted into algebraic expression in the S domain. This concept plays a crucial role in circuit analysis, especially when dealing with complex system and frequency-based behavior.
This is the question we get. The first question is B is for transfer function and G for the Bode plot. Okay, this is our answer for the question B. H omega equals to J omega plus 10 divided by J omega and J omega plus 5 is squared 2. Okay, after that we normalize, we get 10 J omega divided by 10 plus 1, then divide J omega 5 squared 2, and then J omega divided by 5 plus 1 squared 2. Okay, then we get 0.4 J omega divided by 10 plus 1. Then divide J omega and J omega divided by 5 plus 1 squared 2. And then we get, we use the formula and we get H decibel equals to 20 log 10 1 plus J omega divided by 10, then minus 20 log 10 J omega minus 40 log 1 plus J omega divided by 5. After that we get 0 degree plus 10 negative 1, then omega divided by 10, then minus 90 degree minus 210 negative 1 omega divided by 5. There are two corner frequency at omega equals to 5 and 10 radians per second.
Okay, we continue to do the analysis magnitude Bode plot. Firstly, we find the constant, which is the 20 log 0.4. We get negative 7.96 dB. Second, we find the 0, which is the 20 log 1 plus J omega over 10. And lastly, we find the poles. We have the two value we get, which is the 20 log 1 over J omega and 40 log 1 plus J omega over 5. Okay, we go through to the graph semi-log for the magnitude plot. Firstly, to draw the graph, we must draw the constant value, which is K. We get the negative 7.96 at this point. We draw the straight line. Okay, after we find the constant, we can draw the 0. To draw to 0, we use the 20 log 1 plus J omega over 10, which is the cutoff frequency at the 10 radian per second at this point. And after the 10 radian per second, the value will increase until 20 dB at the 100 radian per second and decrease again plus 20 dB, get the 40 dB at the frequency 1000 radian per second. This is the graph of zeros. After that, we find the pole. First pole, we use the equation is poles. We use 20 log 1 over J omega, which is J omega. We replace value of omega in first we put 20 log 1 over 0.01. So what we get negative 40 dB. We plot the 40 at this point. After that we go to 0.1 frequency 120 log 1 over 0.1 20 dB. We plot at the 20 dB. After that we go to the 1 frequency 20 log 1 over 1, we get 0 dB. So we plot this at 0 dB and we continue to 10 radian per second. We go 20 log 1 over 10, we get a negative 20 dB at this point. And lastly we find 20 log 1 over 10, 1 over 100, we get negative 40 dB at this point. And we plot the point, we can see the Z pool is decreased. After that we find another pool which is 40 log 1 plus j omega over 5. This means the cut-off frequency at the 5 radian per second until we decrease to 50 radian per second. This is the second pulse graph. After we complete to find the constant zero and pulse, we can find the total result of this graph. So first, to find the total result, the first result, you can see we take this, we can see the first 40 result. We must total out the value for the each part. First 40 plus with the negative 7.96. So first we got 40 plus negative 7.96. We get 40 plus negative 7.96. We get a 32.04 dB. Okay, we plot at this point 32.04. After that we find this value which is 20 log 20 dB, and we find, okay, at this point we can do 20 plus negative 7.96 and get is 20 log, we can get 12.04 dB. We plot at 12 at this point, 12. After that we find at this value 0 and this value negative 7.96. 0 plus negative 7.96, we get negative 7.96 dB at this point. At this point. Okay, after that we find the value of this at the 5 radian per second. So this and this value, we have the value which is 0 plus negative 7.96 plus negative 14, because in the 5 radian per second we have the 3 graph. Okay, we get 0 plus negative 7.96 plus 40, we get 21, negative 21.96 degree. We at 20 at this point. Okay. After that, we find the value of at the 10 radian per second. We have to do 0, and then we find this point and this point and this point. We have the 4 point, which is, you can see at this point we have the 0 and negative 7.96, and this we assume if negative 13 and negative 20. So we total out 0 plus negative 7.96 plus negative 13 plus negative 20. We get 0 plus negative 7.96 plus negative 13 plus negative 20. We get the negative 40.96 degree at this point. And we plot out the result, and this is the result after we plot the point. Okay, we continue the analysis for the phase Bode plot, which is, firstly we must convert the value of magnitude to the phase. First, we have the 20 log 0.4. So we convert to the phase is tangent negative 1, 0 over 0.4, we get the 0 degree. After that, we convert the value of 0, which is in the magnitude is 20 log 1 plus j omega over 10. After we convert to the phase, we get the tangent negative 1 omega over 10. After that, we convert the value of pole. We have a two value, which is the 20 log 1 over j omega. We get, after we convert to the phase, we get 1 over j omega, which is a negative 90 degree. And lastly, we convert the value of 40 log 1 plus j omega over 5. We convert to the phase, we get the 2 bracket 2 tangent negative 1 omega over 5. Okay, firstly we must draw the constant line, which is the 0 degree. This is the constant line. After that, we plot the value phase of the zeros, which is, we take the middle of 0 is 10 radian, and at this part, which is the starting with 0, after the 1 radian per second is increased to the 45 degree and increase to 90 degrees, and after 90 degrees the graph is constant. Okay, after that we find the value of the poles. First pole is the negative 90 at this point. Negative 90, we see draw the straight line with negative 90. First pole. Second pole is 2 tangent negative 1 omega over 5 at this, which is the center of the point is 5 radian per second at the negative 90 degrees. And before before 5, you can see have the 0.5 at the 0 degree, and this is 50. You can see the 50, the phase is the negative 180, and after we go at the 0 until 0.5, cut off, it decrease down to the negative 90 until we go to negative 180. After that, we want to after we plot the graph constant, 0 and poles, you can find the value of the result. To find the result graph, first we see at this point we have 0 degree and 90 degree. So it's 0 degree plus negative 90 degree, and you get negative 90. So we plot the graph at this negative 90. After that, we find the other value at this 0.5. This point is 0.5 value per second. We have 1, and cut off this. This, and 0 degree plus negative 90. We get same negative 90. You can see this point at negative 90. After that, we find the second value, which is the 0, and we can see at this point we have 1, and this point we have 1, which is 3 points, which is 0 degree plus negative. Yeah, so this is negative 27 degree plus negative 90. So 0 plus negative 27 plus negative 90. This is 117 degree. 117 degree. At this point, 117 degree. After that, we have this value at the 5. On the 5, we have the 1 value, 2 value, and 3 value, which is we have at the constant is 0 degree plus to the 0, which you get negative 90 plus negative 90. 0 plus we get this answer, which is not 0, which is we get this answer. Okay, 31.5 degree plus negative 90 plus negative 90. We get negative 90 plus negative 90 is negative 148.5 degree at this point. 148.5 degree this point. After that, we find the value of this, which is 45 degree. This point, negative 90 degrees, and this point. Yes, so this point is, we have to look. So this value is okay. So we have the 45 degree plus 90 degrees plus, since we have this one, is we assume is the negative 1 we get 45 degree plus negative 90 plus negative 162 152. Of this, and the value of this. So this value we get 162 degree at this point. 162 degree. After that, we check after this answer at the 50 radian per second. We have at this point, and this point. The answer is 76.5 plus 90 degrees plus negative 80 degrees, and 17.5 plus negative 90 degrees plus negative 180 degrees, and we get is the answer is this, which is negative 1 negative is negative the answer is negative 162 degree, negative 93.5 degree. And then lastly we get the last value of this, which is the 90 degree, negative 90 degree, and this last value we get is 90 degree plus minus negative degree plus minus negative 80 degree. We get negative 80 degree at this point. So we can plot the point to get the to find the result, which is this.
My name is Rizati. In this video, I show how to find the transfer function for a pole plot. First, we can see the plot is flat at low frequency, which means there is a pole at the origin, written as 1 over j omega. Then the slope increases by plus 20 decibel per decade from omega equal 10 to omega equal 100. This means there is a 0 at omega equal 10, written as j omega plus 10. After that, the plot becomes flat again, which indicate a pole at omega equal 10. Again written as j omega plus 10 the denominator. Finally, the plot full at minus 20 decibel per decade after omega equal 1000, meaning there is another pole at omega equal 1000, written as j omega plus 1000. So the transfer function is h of omega equal k times j omega divided by the product of j omega plus 10 and j omega plus 1000. From the graph, we know the initial gain is 20 decibel. So we solve 20 log k equal 20, which give k equal 10. Therefore, the final transfer function is h of omega equal 10 j omega over j omega plus 10 times j omega plus 1000. Then how we got the we get the transfer function for a Bode plot.
Okay, let's talk about discussion. Our calculation focus on deriving the transfer function HS and analyzing the frequency response through a Bode plot. We identify the key feature like poles, zeros, and gain, which define the system behavior, and visualize this using the Bode plots. Magnitude and phase response. The plot confirm expect trend, flat region at low frequency, rising or falling slope at critical point. Validating our theoretical analysis, this practical exercise demonstrate how transfer function and Bode plot simplify complex system analysis, making them essential tools for designing and optimizing electrical circuit and control system. Okay, let's go to the conclusion.
The conclusion in this assignment, the concept of the transfer function in advanced electrical circuit was explored. The transfer function, denoted as HS, was defined as the ratio of the Laplace transform of the output to the input, providing a mathematically presentation of linear time invariant system in the frequency domain. The Bode plot was analyzed to visualize the frequency response of the system, showing how magnitude and phase vary with the frequency. Key observations included the identification of poles and zeros, as well as the slope of the plot in different frequency range. The system behavior was interpreted based on this slope, such as flat, rising, or falling responses. The importance of transfer function and Bode plot in electrical engineering was emphasized, particularly for system analysis, control, design, and stability assessment. These tools were highlighted as essential for applications like motor, control, amplifier, design, and signal processing. Through the assignment, a deeper understanding of transfer function and their graphical representation was achieved, enabling the prediction and analysis of system behavior without solving complex differential equations.